Thank you very much. Good afternoon. My name is Urricariet. First time presenting here at LINX, so I appreciate the opportunity. I'm with a company called 26, which many of you probably know us with our other name, Finisar. I've been with Finisar for a long time. Finisar is the largest manufacturer of optical, pluggable optics worldwide, been around for 31 years. And our news this year is that we've recently been merged with a company called 26. So you must start seeing that name as associated with pluggable optics. So that's the only mention that I wanted to do of that name change, potentially for the company and potentially for the products as well. So on into the topics. I'm going to talk about today high-speed connectivity, optical connectivity, particularly around 400G, some of the industry trends around 400G, but also going beyond that, talk a little bit about 800 and maybe a little bit beyond that as well. Let's start with the trends, current trends that many of you know. 400G is being driven primarily by hyperscale data centers and connectivity around hyperscale data centers. Router connections, or rather server connections that are now at 10 and 25G are planning to move to 100G to the server, in some cases multiple 50G or 2 by 50G. Connections between data center racks or inter-switches are going from 100G being deployed today in very high volumes in the big hyperscales to 200G and 400G predominantly at those large cloud service providers. And then long spans, or DCI, where today 100G, 200G coherent, ACO, DCO are being deployed. That will move into 400G coherent, into smaller form factors. I'm going to touch on that as well at the end of the presentation. First, some market numbers, just to show you that, of course, this presentation is about a 400G and that top, pink or orange section at the top, but 100G and 25G still have a lot of the market in optics. So there's still a lot of evolution in price and in volume that will drive optics around 100G for the foreseeable future. And this is the lower numbers, by the way, of Ethernet ports. If we zoom into 800G, into 400G rather, is obviously the big hyperscales that Deloro predicts will drive this growth, as we all know. Google, Amazon, Microsoft, and Apple. The section in yellow show or in green rather, show the second-tier clouds that are coming after that, particularly cloud providers in China, as well as second-tier clouds in North America and some in Europe. And then enterprise shown in orange at the top. So enterprise would only be a small portion of 400G, which is not surprising. So let's get into the actual physical implementation. So what's driving 400G is a 32-port switch supporting 12.8 terabit of bandwidth of switching capacity for those hyperscale data centers, and that's basically what's going to be driving the technologies and the form factors I will talk about in a minute. There's, however, already talk of the line at the bottom there, which is a 25.6 terabit switch, which would have presumably 32 ports of pluggable 800G. And there is some work already being done, early work in the standards, but more likely in the industry with form factors being announced now to support those 800G ports. And I will touch on that at the end after I talk about 400G. Standardization has been going on for several years now, and there's a very wide variety of standards covering 400G. At the top, it shows the early standards which focus on single-mode solutions, both parallel in DR4, as well as a duplex single-mode, FR8 and LR8. I have a slide actually that shows how all these interfaces map much more easily upcoming. So this just tries to show the amount of interfaces being defined both for 400G, next generation 400G, which means 100G channel, as well as multi-mode 400G, which is initially driven by cloud customers in China, the Alibabas and the Baidus of the world, but will eventually be used on enterprise applications as well. The two at the bottom are the two more recent ones, standards being defined both in the CT and CN task force within IEEE, and they're actually for 40 kilometers and for 80 kilometers. So this is a ZR interface which does not exist in 100G as a standard, but we can expect to see it at 400G. Again, a slide coming up which maps all these interfaces into the types of fibers in a much more easy way to see. But lots of variations, single mode, multi-mode, parallel optics, duplex optics, and so on. So there's going to be a lot of choice. The common theme for these interfaces is that they're all based on what is called PAM4 technology. So the modulation is now no longer ones and zeros, but it's rather a 4-level encoding or modulation called PAM4, which basically increases the efficiency of the bandwidth by encoding 2 bits of information per symbol. And that's, of course, done as a trade-off. You have noise, right? So instead of identifying now a 1 or a 0, in the optical domain, we have now 4 levels that we have to clean up and detect, and also at the electrical level as well. So that's the complexity added. There's other interfaces that are not standardized so far, things like SWDM, which will support duplex multimode applications, which will be important in things like enterprise. So we anticipate those will be standardized in the future. Again, more choice for different kinds of 400G interfaces. With regards to the physical implementation of what the modules would look like, there was an early module that few people support, which is called a CFP8. A CFP8 is similar to what a 100G CFP2 used to be in the early days of 100G in routers. So very few core routers and some DWDM transport systems will have CFP8, so you're not going to see it too much. The ones that are actually being now ramping for deployments next year are 2 small pluggable form factors. They are QSFP-DD and OSFP. And they're both coexisting in the market. They're both two MSAs, which companies as Finisar and others are members. QSFP-DD is primarily being pushed by Cisco, Juniper, and some other OEMs. The OSFP is primarily Arista. So you're going to see one or the other form factor depending on which system OEM you speak to. QSFP-DD has the big advantage of the host being backwards compatible, so a future system having a QSFP-DD port will be able to support 100G QSFPs, for example, or even 200G QSFP56. The OSFP form factor is bigger, it's somewhat presumably easier to implement at the system OEM level, although that gap is closing very rapidly. So we anticipate the majority of product offering and even systems offering to support QSFP-DD moving forward, and even Arista is now supporting QSFP-DD ports as well. So again, I promise you this slide. This is how all these standards map into the different fiber types. So if you have multimode and single mode there in the rows, and then parallel optics using MPO, and then duplex using LC. As you can see, there's a wide range of standards, many in the single mode domain, especially things like DR4, which is a 4x100 parallel interface, parallel single mode interface, as well as a DR4 Plus, which is a 2-kilometer proprietary implementation by one of the large clouds in the US. You have also a number of duplex single mode, which again is the preferred interface for this ecosystem of internet exchange. FR8 and FR4 are the early module deployments or module implementations based on 8x50G PAM4, with some of the others coming along next year, like LR4, LR8, as well as ER8 and ZR, which are the 40 kilometers and 80 kilometers that I mentioned. Especially LR8, by the way, is something that we think is a very good solution for the internet exchange applications. It provides a very robust 6.3 dB loss budget, which is similar to what people are using in LR4 at 100G, right? So one of the reasons LR4 continues to have a volume at 100G is that large loss budget that is good to go over multiple cross connects, for example. So LR8 will be that equivalent, and that's something that's already in the market by several suppliers, not only ourselves. And again, the form factor is kind of orthogonal to this. All these interfaces could be implemented in any of the 2 form factors. We see QSFP-DD having a bigger momentum in the industry right now, but again, an OSFP ecosystem might develop for certain applications. You see multimode there at the top. As I mentioned, parallel multimode is being driven today by those clouds in China. There's also a large cloud in the US, actually Google. They were kind of pretty public at the IEEE supporting SR8. And those interfaces can also be used for breakout applications. And I'll get into breakouts and the importance of breakouts later in the presentation. So those are not only point-to-point, but could be used in multiple 50G connections to next-generation servers, for example. The top right quadrant, duplex multimode, again, no standardization going on so far, but that's important for enterprise, right? Enterprise always wants to reutilize the fiber plant they have, and that's duplex multimode in their case. Just very quickly, it's a typical block diagram of one of the early implementations of 400G, in this case FR4 2-kilometer module and transceiver, regardless of the form factor. Again, this could be in a QSFP-DD or OSFP. So this has a, it will have a 8x50G electrical interface called 400 GAUI 8 by the IEEE, and then the optical interface. You know, the one gaining more momentum in this case is FR4, which is the CWDM4 equivalent, right? Duplex single mode over 2 kilometers, 100G CWDM4. The equivalent of that at 400G would be a 400G FR4. And these initial modules will have what's called a gearbox. Some of you remember that at 100G. So this 8x4 max, that will be the equivalent of a gearbox that these modules will have. And we're going to see later on how that will go away in subsequent generations, which is a good thing, right? Just like it happened at 100G. So how this will be implemented in a typical cloud data center, and this is kind of like a general way of describing an architecture, and that could vary over the, different hyperscale clouds. But in blue there I show how the current ecosystem of 25G servers and 3.2 terabit switches are implementing the optics, so no surprise here. 25G SR to the server, 100G SR or active optical cable. CWDM4 100G is what most of the clouds are implementing today, as well as 100G to 100G coherent. The way this will evolve, we anticipate will be somewhat similar. So when we go to 50G, 100G to servers with 400G interswitch or 12.8 terabit switches, we see essentially a very similar kind of implementation, with maybe optics taking a bigger role on the rack to the server, just because at 100G per second copper will have a very, very short reach. So we foresee copper taking less of it, so copper DACs. And there are people out there that have shown copper DACs already. However, they're extremely thick and very hard to manage in any kind of significant density inside a rack. So we foresee copper not playing such a major role. So active optical cables, as well as regular SR optics. Then DR4, SR4.2, going from top of rack to leaf, perhaps even eliminating the top of rack switch in some cases. And then again, single mode, in this case, the equivalent of CWDM4, FR4, maybe FR8 at the beginning, as well as then duplex single mode for inter-switch or inter-data center rather. Direct detect up to 40 kilometers, and then ZR coherent optics playing a bigger role, we believe, with higher density ports at 80 kilometers and even 120 kilometers. So the ecosystem is very active about this. If you go to any optical show like OFC or like ECOC in Europe, you're going to see a lot of different suppliers as well as MSAs doing a lot of different demonstrations, many interoperability demonstrations. So the ecosystem is evolving very nicely with multiple suppliers, both at the switch level and at the module level, at least showing their hardware publicly. So what happens after that? And even within the context of 400G, many people ask us, is pluggability still a requirement for optics, right? There's a lot of talk about onboard optics, and so far it's just that, it's only talk. Going away from pluggability with higher density. Microsoft is very, parts of Microsoft at least are very public with COBO and other things. So non-pluggable optics, what's called onboard optics, have been around for quite a while in the supercomputing space. Maybe over 10 years, maybe 8 to 10 years ago, implementations of non-pluggable optics, VCSEL-based, multimode-based, and where there's a couple of suppliers, Finisar being one of them, that are the large players in that space. The value of that is that, of course, you have something that sits on the board with very short traces, so the power goes down, the way you drive the signals go down. That allows you much higher bandwidth densities with much lower power. Of course, you lose pluggability, which for pay-as-you-grow implementations is not a good thing. So the supercomputing market adopted it. The regular Ethernet market is reluctantly looking at it because, again, that lack of flexibility of using pluggable optics. So obviously you can get much higher throughput. The state of the art today, by the way, is 25G per channel in a 12 or 16 channel configuration in a 1 inch by 1 inch block. Again, that's based on VCSEL technology, so very short reach, 50 gig per channel, so 16 channels by 50 gigabit per second per channel is being developed and being implemented in those supercomputers. Our view, however, for Ethernet, for the communications market, is that pluggable optics will be preferred, obviously, at 400G, I mentioned that already, but also at 800G. And there is talks will 400G be the last generation for pluggable optics? We do not think so. The industry doesn't appear to think so for the most part. So the view now is that perhaps non-pluggable optics will play a much larger role after 800G. Will presumably be 1.6 terabit. 1.6 terabit. One terabit, we think 1 terabit is probably not enough, right? Because there's a lot of investment in next generation. So going from 800 to 1 terabit is not enough. 1.6 we think is probably likely the next step. So that might be, a lot of that might be non-pluggable. So 800G. Pluggability we think will be prevalent as well. There's a new MSA that has been announced and formed recently. It's called the QSFP-DD 800 MSA. Some of the same characters, as you can see there, Cisco and Juniper, as well as many of us in the ecosystem, are starting to define the QSFP-DD 800. The premise is to keep the same size as the QSFP-DD, improve the thermal management design to be able to support up to 24 watts. Today, a QSFP-DD can support either 15 watts or more recently 20 watts with a new type of QSFP-DD called the 2A type. In the case of 800G, the aim is to support up to 24. And that would mean that a module could support a dual 400G application. At least for first, second generation, 400G modules are expected to be around 12 watts of power. So this would allow a 2x400G. And that's exactly the application that this module, early on, this module will be focusing on, right? 2x400G and also maybe high-density 100G, 8x100G in a single module. At some point, maybe there will be a standard, but there's not even a talk of an 800G MAC at the moment. So what are some of the technologies that are happening in the industry which will enable such modules such as I showed? One of them is electrical channel running at 100G. And the IEEE is already standardizing this in the CK task force. So this means single electrical lane running at 100 gigabit per second using PAM4 electrical, using PAM4, which means 50 gigabaud, which is significantly higher of what people are implementing today, 50 gigabaud signaling. So this would enable much higher bandwidth density and cost-effective transceiver form factors. For example, a 400G true QSFP, not a DD, but rather a QSFP 112, the equivalent of a QSFP 28, running now at 100G electrical per channel, so much smaller in size and in power. You eliminate that gearbox that I mentioned, right? That gearbox that's inside a QSFP-DD will go away. A 100G SFP. Today, your servers have a 10G SFP. It's a very small module. 25G is probably there. It will be the next wave of server connections. After that, 100G directly into a server with a very small module. That will also be enabled by 100G PAM4 electrical, as well as, of course, the 800G DD that I just mentioned. That would have an 8x100G electrical interface into the host. That, again, all of this will eliminate the need to use a MUX-DMUX inside the transceiver, which, of course, reduces cost, complexity, and power, and that's generally a good thing, and that's what happened at 100G as well. Those of you that remember the early CFPs and CFP2s with a gearbox. So we're talking, the timeline for this is very soon, actually. We're not talking 5 years from now. The CK timeline for 100G electrical, it's approximately a couple of years, actually. Major change completed, expected in March of 2021. That's the latest timeline adopted or published by the task force at the IEEE. The other enabling technology, which is maybe less relevant for this ecosystem, the IX ecosystem, is 100G PAM4 VCSELs, which means very cost-effective multi-mode connections that will drive enterprise, will drive parts of cloud as well. So far, VCSELs have been supporting up to 25G per channel. 50G per channel is starting to be shown and deployed, not deployed, but qualified by customers or by system OEMs. This is a 100G PAM4 VCSEL, which is a VCSEL that runs, again, at 100 gigabit, 50 gigabaud, which would enable things similar to the electrical I/O. For example, a 100G SR SFP, running at a single VCSEL, running at 100 gigabit to connect to servers. 800G SR8s, 800G SR4.2. Again, you get it. The ecosystem for multimode, which is important for any kind of ecosystem to gain adoption at the enterprise level, people actually using and data centers driving the volume, are starting to be feasible. We demonstrated the first one. There are others working on it. Obviously, this is nothing proprietary, but so far it's very, very leading edge, if you will. So you wouldn't anticipate to see this in the market until maybe probably 2 to 3 years from now. And there is standardization work today. Actually, this week, the IEEE is meeting in Hawaii, of all places, and they will probably agree to a new study group for multimode 100G, single channel 100G optical standard. So the other aspects of that is breakouts. And somebody mentioned edge and how breakout applications at the beginning, I think it was Juniper earlier on. All of these interfaces, and I'm not going to go to the table in detail, but it'll be there for your reference. All of these connections and standards, both at 100G, 400G, and at some point 800G, would enable a large variety of breakouts from those 32-port switches. Either 25G server breakouts, 50G, and even 100G server breakouts in different form factors and different power levels and reaches and so on, which will be a very good thing as we said, the edge deployments of data centers will require this variety of applications in the field. So that the ecosystem is actually being formed to support all those kinds of applications. If we get to edge, by the way, and again, Juniper mentioned today, low latency applications for AI and IoT in the edge, that will change also some of the requirements for performance of the optics themselves. The connectivity at the edge data center will require maybe lower bit rates, not as high as the hyperscale data centers, obviously. It will require high radix breakout, and when I showed in the slide before how this is being formed, with maybe applications of 2 kilometers or 10 kilometers, right? Because again, those servers may be further away from those edge data centers at the customer premise. It will require small and higher density server and switch form factors, obviously. Some space may be constrained at both the edge data center as well as the customer premise site. And, of course, extended environmental performance, right? As the edge becomes further and further away, uncontrolled environments, and pedestal even, micro data centers in a pedestal at some point may become the norm, so the optics will have to meet those performance requirements. And, of course, the access networks in the telecom space have already given us guidance how to do that. And these requirements obviously will change over time as the edge changes, right? The edge is going to be, go deeper and deeper, closer and closer to the customer, to the client. So how do we get to the edge? So similarly, DCI applications today are using Coherent. We anticipate Coherent will play a large role in the edge as well, maybe at the lower rate, maybe at 100G Coherent. So today, as I mentioned, those interfaces are running at 100G and 200G. At 400G, the good news for DCI is that standardization is happening. So both the OIF has completed also an implementation agreement for 400G coherent interfaces to around 100 kilometers, and the IEEE is now homologating that, as I mentioned earlier, in the CT task force for a 400G base ZR interface, single channel coherent tunable DWDM transceivers. So that ecosystem is actually forming very nicely as well, is being enabled by technologies such as next generation optical packaging, led by the OIF and many of us in the industry, as well as next generation DSPs, which are based on 7 nanometer CMOS, which would enable the size and the power required for this very small form factor pluggable coherent modules. So the way that we see those optics evolving is from the model that we have today, which is essentially a transponder model where you have people like the Ciscos, the Huaweis, and PacketLight, Infinera, having these 1RU transponder boxes using CFP2 ACO and DCO, moving into a model where at 400G, a true pluggable DCO solution that can go directly into the switch will be feasible, into a switch or into a router. So in essence, eliminating the optical layer, eliminating the transponder box, and enabling those switch ports or router ports to go 80 kilometers, 120 kilometers using 400G coherent optics. So that ecosystem is developing nicely. It could also be an OSFP, and we anticipate these modules to be out there in the 2020, 2021 timeframe. So that's all I had today. I appreciate your time. I'm not sure if we have any time for questions. No questions? Okay. All right. Thank you very much.